then it works.
Yeah, I did this past summer.
Yeah.
My first college
I know. I was honored, right? It was your first college experience, and we made it through. So, okay. So, are there any questions on limits? Because we went through it kind of fast on Tuesday, so I want to make sure that there's an understanding of what it looks like. So remember, there's two different ways to look at a limit. You can find it graphically. So graphically means what? On a graph, right? You're just picturing it. Okay, so there's a graph. Does the limit exist? Let me ask you that from this one. At x is 3, does the limit exist?
No. Well, yeah, it does. Your fingers don't meet.
Right. So remember, it's all about the meeting fingers, right? So the difference between algebra and calculus, algebra is all about what's it approaching, what's it heading towards, okay? Because we're basically looking at a moving target. We're looking at what is happening as I approach 3. Well, I'm approaching 1/2. It doesn't equal 1/2, but I'm approaching it. And that's the difference between calculus and algebra. Calculus is all about what's it approaching. Algebra says what does it actually equal, okay? So it kind of opens it up for us. There's right-handed limits. So like on this one, there's right-handed limits, which means which side am I going to come in from? The positive side. So I'm going to come in here. Now, if I'm heading towards -1, and I'm coming in from the right, this side of the graph does me no good, right? Because I'm not coming in to -1 on this graph. I'm only coming into -1 on this graph, okay? So I'm heading in and I'm heading towards 4. So the limit coming in from the right does exist, right? The limit coming in from the left also exists, but the limit coming in or heading towards from both sides, it does not exist. So I can have a right-hand limit, I can have a left-hand limit, and I can have a does not exist, all right? Now, what's the limit as x approaches 2 from the right? Okay, so I'm coming in from the right, I'm heading towards 1. How about coming in from the left? Okay, I'm coming in, I'm heading towards 1, and so from both sides, I'm going to the exact same spot, okay? So a limit is always going to be your y value, right? We are looking at what's happening at the x value, but we're heading towards a y value, okay? All right, so what we're going to do next is what's called continuity. So you have one of these, and I attached some graphs to it. So kind of, you have 6 graphs. So lay out those 6 graphs that are attached to it's this one. There should be 6 graphs, they're all cut up. So take those off, lay them out, take a good look at them. So continuity means, is it smooth and is it continuous? That's what we're looking for. Is it smooth and is it continuous? The other thing about limits and continuity is it all depends on where we're looking on the graph, okay? So when I look at this graph over here, I have a limit that doesn't exist. But if I look at this over here, I have a limit that does exist. So it's all dependent on where on the graph we're looking. So you have to be very specific at a very specific point, okay? So continuity is defined as smooth and continuous, all right? So if I were to run my finger along this graph, I'm good, it's smooth, it's continuous, I'm never lifting my finger up, right? Until I get to here. I have a jump, right? There's a hole there. So that means if you think of it in terms of I'm on a road, right? You're on a bicycle. I'm on a bike, it's smooth, it's continuous. I hit this hole, what do I have to do? I have to jump, right? Can't go through it, I gotta jump it. So what happens to my finger? It leaves the graph, right? So it jumps across the graph. This is not continuous. It is continuous and smooth here. So it's continuous and smooth here until I hit this point. and then I jump, and then I can continue, and it's smooth and continuous. So again, if I said, is my graph continuous at x equals 2, my answer would be yes. But if I said, is my graph continuous at x equals 1, I'd have to say no. Okay, same thing here. If I go here, when I get to -1, I have to jump to get to the next graph down. Okay, so smooth and continuous is continuity. All right, now there's 3 rules that apply with continuity. The first one is you have to have a definition. The point has to be defined. Okay, so there's 3 things that we have to look for. So that's your first one. Oh, and what I did is, and you can fold this or not. Actually, it might be better if you folded it. So it doesn't fold exactly, so it's going to look like this when you fold it. So you're going to have this continuity is visible. So you kind of fold it on the black here and then fold it in like this. Okay, so these are our 3 rules. The first one is the point defined there. So when I look at this one, if I said, and it's got to pass all 3 of these rules. So if I said, is the value at 1 defined? On this particular graph, is the value at 1 defined? What would you tell me? Does it have an actual point at x equals 1?
Yeah.
It does, right? It's here. So it is defined. It does have an actual value sitting right there. If I asked you, is it defined at x is -1, what would you say?
Yeah.
It is also, because it's defined right here. Okay, it's not defined here, but it is defined here. So it does have a definition. It does have a value right at that point. So that's the first rule to pass. The second one says, does the limit exist? Okay, that's the second one. So if I'm looking at x is +1, do I have a limit that exists at x is 1? Do my fingers come to a point? Do they come together? They actually do, because I'm heading towards 2. Okay? So, or you can do it, I have a right-handed limit of 2, I have a left-handed limit of 2, so I have a limit that exists at 2. Even though there's a hole there, it's getting close to 2. And remember, that's the whole idea, is what is it getting close to? Okay? So it does exist here. Where over here, if I said at -1, the limit does not exist. All right? So if I'm talking about -1, I would say it is discontinuous at -1. It's continuous at 1. So it passes number 2 here. It does not pass number 2 here. You see the difference? Okay? So if I'm talking at x is 1, it is defined, and the limit does exist. All right? I passed 2 out of the 3 rules. Okay? The third rule says the definition of the point and the limit have to be the same. That's what number 3 is. The limit and the definition have to equal each other. If one of these rules falls apart, then that means it's not continuous. All right? Now, visually, we can see it. We can see that it's discontinuous here because it equals 4. It's a limit of 2. They do not equal each other. Okay? So it passes the first one, passes the second one, fails the third one. So that means it's discontinuous. Okay? So that's what you want to look for. You have to go through each one and see where does it fail. So what I want you to do is I want you to look at A. Look at the graph at A. They're up here, the letters. All right? And I want you to mentally walk through all 3 rules. Is it defined at, and we'll do x is 0. So is it defined at x is 0?
Yes.
Okay, what does it equal?
0.
0. Does a limit exist at x equals 0? What is it? 0. Is 0 equals 0? Yes. So it's continuous at x equals 0. Okay?
So then where do we put it?
Okay, so we'll get there. We'll get there. So what I want you to do is now I want you to go through and I want you to find one graph, one of those 6 graphs, and figure out which one does not meet condition 1. Just condition 1, that's all you have to look for. Just find one of the graphs that does not meet condition 1. So condition 1 says, is it defined? Does it have an actual value? It doesn't say. Well, let me see what you guys come up with. Let me see if we can do it that way. So look at the graphs and see, is there any place where a value is not defined? And there might be more than one. Which one do you have? D. Okay, so explain it.
It looks like at 4, I mean, those lines, they're going to continue to get closer but never touch.
Okay.
So they're not, there's no value at x equals 4.
Okay, and do you know what that's called? When it
Oh,
approaches but doesn't touch it?
I remember it's
Starts with an A. It's a weird word. It's called a vertical asymptote.
yes.
Okay, so it's a vertical asymptote, which you don't need to know that, but you know, it's a term you might show up. Can you see any other one where it fails rule number 1?
Maybe B.
Okay. So, and that's a couple different ones, right? At pi over 2, and then at 3 pi over 2. Okay, those two are both vertical asymptotes. Good. Okay, so you can write that in the middle where it says, write the letter, or you can attach it. I have tape if you want to attach the graph. So it's graph D at x equals 4. So graph D at x equals 4. Okay. Okay. Now on the next one, I want you to write the letter or letters, there's more than one, that meets condition 1 but fails condition 2. So in other words, it has a value, but the limit does not exist. So see if you can pick up 2 graphs where it meets condition 1, but it fails condition 2. So it has a point, but it doesn't have a limit at that point. Can you see any of them? Okay, so with the first one, right? So we have a vertical asymptote right here, right? So there's no point.
But it still has like points right here and right here.
Right, but if we're looking at a very specific point, if we're looking at x is 4,
Okay.
it doesn't have a value there. So we're kind of looking at the whole thing to see if there's
Yeah.
any place on the graph that it
So
doesn't.
as long as just somewhere. Okay.
Yeah, and then here, see it has a vertical asymptote here and it has a vertical asymptote there. So there's no values there.
Okay.
Okay, so now this one, and this kind of gives you an example. We have a point that exists,
Yes.
right? But the limit doesn't exist. So it passes rule 1, but it fails rule 2. And rule 2 says it has to have a limit. The limit has to exist.
Okay.
Okay, so now see if you can see, and there's more than one to pick from. So a point that exists, but the limit doesn't exist. What did you find?
I was thinking probably that one.
Okay, so
Because, I mean, there's I mean, it's the first condition, and then there's, like, no, there's no, what am I looking for? Limit.
the limit.
I mean,
So, okay,
Right.
so when we talked about this one first, right, the limit does exist at 0,
Oh,
right?
okay, yeah.
So we do have limits, and every single one of those, you know, x is 1, x is 2, x is 3, we can come in from both sides,
Okay.
right? So what you want to
Oh,
look
okay.
for is a point, but where a limit doesn't exist. So Joanna, do you have an idea? Okay, f, and at what point?
If it could be, this one could be defined,
Mm-hmm.
and this one doesn't exist.
Okay, good, yeah. So f at x equals -2. So look at graph f. Okay, so do you see the point exists at x equals -2? So what does it equal at x equals -2? On f. Okay, it equals 3, right? So it passes rule 1, but at x equals -2, does the limit exist? You see how it comes to 2 different points? You see it? It goes to 3, and then it also goes to -2. So good, Joanna. Okay, can you find another one? C, okay, so take a look at C. So go ahead, Nicholas, explain it.
Well, x equals -2 again, it's actually -4.
Mm-hmm.
It comes here, that looks like right in the middle, so like at +4.5, and then on the other line, it's at -2.
Good. So because it's coming in right and left from 2 different, or it's heading towards 2 different points, the limit doesn't exist. So it passes rule 1, fails rule 2. Okay? Are we good? Alan, you're good?
A little bit.
Okay, so here's, so rule 1 says there's a point there.
Mm-hmm.
Okay? Rule 2 says the limit has to exist at that point. Wait, where am I?
Okay,
This
so
one.
when you
This
say
one.
limit, what are you looking for?
So the limit means my fingers are coming together.
Okay.
So it does exist,
Mhm.
and when I come together, see how I'm going to
Yeah.
2 different places? So the
Okay.
limit doesn't exist.
Okay.
And then same thing here. There is a value there,
Mhm.
so it passes rule 1, but when I come together at -2, my fingers are going to 2 different
Okay.
places.
Okay.
Okay?
Alright. That's what I was. See, I didn't know what I was looking for when you said point or.
Where the limit
Yeah,
exists.
the-
Oh,
the-
so
the
this one is
defined,
defined.
yeah.
That means there's an actual point
Okay,
there.
okay.
So like
So-
this one, there's an actual point there. There's an actual point there
Okay.
at that particular point.
So basically, it would pass, so to get the, for number 2, to have the right answer, on the thing before, it would pass from the negative side, and it passes from the positive side, but it doesn't pass from both sides.
Correct. Yeah, it always, for the limit to exist, it has to come from both sides.
Yeah,
Okay?
It doesn't have like a negative or positive.
Mhm.
It has to go from both sides.
Right.
Not just like
Right, so your fingers have to come together from both sides for it to exist, okay? All right, so now, number 3. I want it to pass condition 1, so it has to have a point there, and it also has to have a limit. So both of those conditions have to meet, but then it's going to fail condition 3, which means the point and the limit are the same. So if it fails condition 3, that means they're going to be 2 different things. So which graph? Take a look. Let me see what you got. What'd you get? E, okay. E, okay, and Joanna? E, okay, good, yes. So the value at, oh, I'm looking at the wrong one. The value at -2 is -4. The limit exists, and what is the limit? What's both sides heading towards? -2, but they're not the same. Okay, so it fails. So this is another idea of continuity, okay? All right, so that's just kind of the gist of continuity. You just need those 3 rules. So now grab that worksheet that I handed out, because we're going to look at it from different perspectives. So we're combining continuity with finding a limit, okay? So look at they were supposed to go back to back. So look at this page right here. Okay. There we go. Okay, so this one is just those 3 rules again. They're in different order, but they're the same 3 rules. Number 2, it exists. Number 1 says the limit exists. And number 3 says they're the same thing. All right, now what you're having to do is you're having to learn to read math, right? Those are all math symbols. It's not written out, so you have to understand what they are talking about. So your visual examples, In the middle of the page, you have a continuous. It's continuous at 3. The middle one says it's discontinuous at 3. So which rule did it fail?
The middle one,
This middle graph right here, which rule did it fail?
the limit equaling, so limit of f of x equals 1.
So it failed rule number 3. Okay? The limit exists. The value does exist, but they're not the same thing.
So for it to be, so limit and point equal each other. So if it was to be 3 and 3, it would pass that rule?
Yes.
Okay.
Yeah, so if that black dot was right there where the open hole is, then it would pass. It would be continuous, yeah. Okay, and then the third one is discontinuous at 3. And which rule did it fail?
That a limit exists.
The what?
That a limit exists.
Right, that a limit exists because it's coming to 2 different places. Okay, so what I'm going to do for your test is I'm going to give you something like those, and I'm going to ask you which rule fails. Okay, so you have to go through the 3 rules in your head and go, okay, this one, like on that third graph, it exists at x equals 3 at 4. The limit does not exist, so it's going to fail that, well, in this case, it fails number 1. Okay, so now you do it. Those 3 graphs at the bottom, and you can use the order up here since it's just sitting here. Just use this order. So you can say fails number 1, fails number 2, fails number 3. Which one do you think it fails? Okay, Casey, what'd you get for the first one?
Fails number 1.
Okay, okay, I was thinking the,
Yes.
okay, from this one, yes, okay. So it fails that the limit, it doesn't exist. So everyone agree with that on the first one? Okay, Joanna, what about number 2? Or the middle one?
I don't think one fails.
Okay, so remember 1 says that the limit exists. So if you put your fingers on that line, they're going to head towards the same point, right? So that means the limit does exist, right? So number 1, it's good. It passes number 1. Does it pass number 2? Is there a value? Okay, so the value does exist. And then are they the same thing?
Oh no.
Okay, good. So it fails number 3. The limit exists, the value exists, but it's not equal to each other. So it's going to fail number 3. Okay, Alan, try the third one.
Let's say that would be number 3. Maybe.
Okay, so go through each one. Is there a limit?
Yes.
Okay, and is there a value that exists there? Okay, so it fails
Number 2.
number 2. Good. So it fails number 2. Okay. All right. So now go to the next page. Oh, go ahead.
If it fails number 2, it also fails number 3.
Exactly. Yeah. Yeah. But all it needs to do is fail 1, and then it's discontinuous. Okay. All right. So now go to the next one. So you're going to use that that graph. So this is an example of it depends on where your x is approaching. So if you look at example 1, they're all approaching -1. When you look at example 2, they're all approaching +1. When you look at example 3, they're approaching 2, and example 4, they're approaching 3. So every single one of those are going to have a different answer because I'm only worried about, in example 1, as it's approaching -1. So this is like what we did on Tuesday, so it gives you a little more practice being able to graphically find a limit. So A says you're approaching -1 from the left. So again, the right side of the graph means nothing to me. I don't even have to look at it. All I want to do is look at that, what's going on at -1. So what is the limit as x approaches -1 from the left? 3, good. Okay, does everyone see it? Okay. And then B says approaching -1 from the right. Also 3, good. Okay. And now C says approaching -1 from both sides. 3. So do you see the little hint there? If it comes from the left and it comes from the right and it's going to the same place, that means the limit does exist at that same place. You don't even have to go back to look at the graph, right? You can just automatically go, oh, well, if it's going to the same place, right and left, it's got to be meeting in the middle. Okay, so D is asking the algebra question. What does it actually equal at -1? -1, good. Yeah, so this way. So now, yeah, so we came from the left side, right?
Right.
Oh, I'm sorry, this way, so it approaches 3.
3. Okay.
And now from the right side?
So that'd be right there, right?
Well, no, because it's going towards
Okay.
-1. So you just want to, you kind of want to just concentrate at -1 and then come in from the right side. So where is it heading towards?
So 3.
Uh-huh,
Okay, so 3.
yep.
And that's going to be your y, right?
Mm-hmm.
Okay.
Yeah, and then this is saying from both sides. So since these are already equal, you know it's got to be 3 again,
Okay.
right? And then this is saying, all right, what does it actually equal? That's your algebra
So
question.
negative would be -1.
Mm-hmm. Yeah.
Oh, okay.
Okay. All right. So then E. Now we're into the continuity. Is f continuous at x equals -1? And then tell me why. Okay, it's not. And which rule did it fail?
The limit as x approaches -1 is not equal to the actual value.
Good. Yeah, so it fails rule 3 because the limit and the actual value are two different things. Okay? And again, you can see it, right? You have to lift your finger up, jump down to -1, and then jump back up to the graph. So that's that continuity. It's not smooth and continuous. Okay, example 2. Go through it, and then we'll talk about the answers. Okay, so Casey, what'd you get for example 2A?
1.
Okay, and Joanna B? Example 2B?
This is the positive sign.
Right, so it's so you're coming in from the right, heading towards +1. So where is it heading towards?
This.
Uh-huh.
I think it would be 3.
You're heading here. Sorry, not to this one. Here's 1 here.
Okay.
1, yeah. Okay. And then Nicholas, C. Okay. And again, just like in example 1, if it comes in from the right and it comes in from the left, then, and it's going to the same place, it's got to be. All right, and then Alan, what's it actually equal?
What is f equal?
What is, yeah, at x equals 1, what does it equal?
1.
Mm-hmm. Okay. And then is it continuous at 1? Yep. The limit exists, the value exists, and it's the same thing. So it passes all 3 rules. Okay? All right. Any questions? You good? So go ahead and do example 3 and 4, and then we'll jump to the equation ones.
I have a question.
Okay.
On D, there's no value up or down at all, so it's just this. Okay.
Yep, good.
Okay, so for some, it's not sticking. I don't know why. But,
Okay.
okay, so for this one,
Mm-hmm.
it'd be as x, because it's a negative, right? So it's coming in from the left.
Right, so it's coming, but it's heading towards positive 1.
Okay, so you're
Uh-huh.
looking at this one?
Yep.
Okay, so it's where the point is.
Mm-hmm. Yeah, it's your y value. What's it? It's heading towards that y value.
Okay,
Yeah.
so then this would
But
be.
then this one, you're coming in from the positive side. So over here, it doesn't help me, right? Because this only goes from, where is it? From 2 and up, right? I want it to go to 1, so I have to go to here,
Okay,
right? So it's coming in this way. Where is it headed towards? Or this one?
for 1.
Mm-hmm. Yeah, so this one would be 1 also.
Okay, so that'd be 1. So, okay, so as it approaches 2,
Mm-hmm.
so where's 2?
So here's x is 2.
Okay, so then it'd
Mm-hmm.
be 2.
Mm-hmm.
Okay.
Yep. And then this is coming in from the positive side.
So it'd be here?
Well, okay, so here's, this is, let's see, where are we? This is 1, 2, right? But if I'm coming in from the positive side, this graph doesn't do me any
Right.
good, right? I have
Okay,
to
so
jump
it'd
here.
be- Okay,
So it's heading towards what?
4. Or what is that? 1, 2, 3.
3, yeah. Okay, so then coming into both, from both sides,
It'd be
see how it's coming to 2 different places?
Yeah.
But it's heading to 2 different places, which indicates here.
2 and 3.
Mm-hmm.
Okay.
So since these are different, right, my fingers aren't coming together.
Mhm.
So this is the does not exist, the
Oh,
DNE.
okay.
That's where the
Okay.
DNE comes in. Okay,
So at 2 it equals
where the dot is.
with the dots.
Mhm.
Okay, so it'd be 3 as well.
Mhm. Yeah. And so is it continuous?
No.
No, because there's a
Because
jump
there's-
there,
yeah.
right? Yeah, and or you could say it fails because the limit does not exist.
Okay.
Okay, so even though it exists on the right and the left, it doesn't exist together, and that's the only thing that you want to worry about.
Okay, so these are just the different these right here, right?
Well, these are you're finding the limits, and then
Right.
the continuous is you go through the 3 rules and go, okay, so there is a value,
Mm-hmm.
right? But the limit doesn't exist.
So it'd be no.
So it wouldn't be no, yeah.
Okay.
Okay, so now walk through those
So
three.
it's coming from the negative
Mhm.
from the left side. As
And
it
it's heading
approaches
towards 3.
Let's see, where's 3? 1, 2, 3.
No, on X.
Oh, okay, next. So
Mhm.
it'd be this one?
Mm-hmm.
So then it'd be 1, 2, 3, 4.
Yep.
Okay. And coming from the positive. Would be this one.
So where's 3? Where's
Three.
X equals 3?
Oh, okay. See, I keep mixing it up with. Right here.
There we go.
So then it'd be
Yep.
this.
Mm-hmm. So that's
Okay.
4 again.
So I'm just looking at the X, right?
Yes.
Okay.
Yep.
That makes more sense.
Yeah. And then your answer is your Y, and that might be the
Okay.
confusion,
Alright.
yeah.
Yeah, okay.
Okay? All right. Okay, so example 3, A is 2, B is 3, C is does not exist, and D is 3. Everyone good? And then it's not continuous because it fails the limit. There's no limit that exists, so it fails it. Okay? And then example 4, we have A is 4, B is 4, C is 4, but there's no value at 3. You see it? There's no solid dot at 3. So it's not continuous because it fails having a value that exists there. Good? Okay. All right. Go ahead.
Just undefined word? Or would it just be no solution?
On E?
Well, on D.
Oh, on D. Yeah, it would be no solution, does not exist.
Okay.
Yeah.
Okay.
Undefined? No, undefined would be if it was over 0.
Okay.
So that wouldn't work. So it's either does not exist or, what was the other term I said? I forget. So, okay, so what I wanted to do is I wanted to show you graphically these next two, or yeah, the next two. So example 5, so now we're gonna do this continuity thing with a function, right? A piecewise function. So remember, a piecewise function means it's two functions put together on the exact same graph. I'm going to put this back up so I can draw on it. And the first function, x squared, is only when x is less than or equal to 1. So here's 1 right here. So here is a solid dot, and it goes this way. Okay, so all of this is gone. And then the line is 2x when x is greater than 1. So here's our line. You'll see where it is. So it's here and going up. So all of this is gone. So those are our two spots, right? And then it's going to be an open circle over here. I don't want to write on the wrong board. Okay, so it's an open circle going up. And goes to here. So there's our parabola, and then the line goes like that. Okay? So that's what it looks like. So I want you to be able to put the graph and the equation together. Okay, so determine all points of discontinuity, if any, and discuss the behavior at these points. So in other words, why is it discontinuous? Right? So algebraically, this is how you're going to do it. You're going to base it off of that x is less than or equal to 1. So the limit, so we're going to do it this way. The limit as x approaches 1 from the left of this function. Okay, so which equation are you going to use? The top one, the first one, or second one? The first one, yeah, because it's everything less than 1, right? So when I plug 1 in, I get 1 squared, which is 1. Okay? And graphically, it makes sense. If I come in from the left side, I'm approaching 1. Okay? The limit as x approaches 1 from the right of the function, what's that one going to equal? So you're going to use the 2x, right? So 2 times 1 is 2. Makes sense. Here's 1 here. Here's 2 here. I come in from the right, and I'm approaching 2. Okay? So what does that automatically tell you? It's discontinuous because of why? 2 different points. Well, it does have a value, so we're good there. But what fails is the limit doesn't exist. Okay, because there's no limit, right? I'm coming to 2 different places. So this one is not continuous, or it's discontinuous, because it fails whatever rule that is. Number 1, it fails that the limit exists.
You gotta fix the number 1 and 2 on this. Because they're different.
Right, because we're using a different value.
Well, I mean, like, the number one.
Oh, okay, gotcha. And this, yeah. This came out first. This I found and I liked it because it was different. And it kind of compacts all the information. So, okay. So we have the second one. I'm not going to rewrite it. So now we're talking about, now we're looking at when x is 2. Okay. So now our graph is going to change a little bit. So we have 1, 2, 1, 2, 3, 4. So we have goes like that. 2 times 2 is 4. And then goes like that. Okay, now I exaggerated this, right? Because now we're talking at the same point. Okay, it equals when x is less than or equal to 2, but it's greater than when it's 2x. Okay? But do you see it's the same point? Right? When x is 2, the line is 4. When x is 2, the parabola is also 4. So it kind of works out that way. Okay, so let's just look at it. Does the limit exist? It does, because it's going right to the same spot, right? Now, algebraically, what you would do is you would look at it and you'd go, okay, the limit as x approaches 2 from the left, the limit as x approaches 2 from the right. If these are the same, then the limit exists, right? So from the left, you're going to use the top one, so x squared, which is 4. If it's coming in from the positive side, you're going to use 2x, which is also 4. So right there, that tells you that the limit exists. Because these are the same. Good? So we have a limit that exists, so it passes that rule. We have a point existing, so it passes that rule, and they're the same thing, right? If I said, what's the value at x is 2? Well, it would be 4. So because these are the same values, then our limit does exist, our value does exist, and so because they're the same thing, we have a continuous function. Okay? Even though this is supposed to be open here, it's actually got a point right there also. So it kind of fills in that gap, right? So we have a continuous. Okay? Good? All right. So what we're going to do tonight is we're going to finish with what's called the difference quotient. So I'm trying to think. Joanna, do you remember, or Nicholas, did we do difference quotient in 1314? Maybe not the term that you remember. I can't remember if we did it or not. Okay, so let me show you what it is, and then I might jog your memory. So I'm going to start with quotient. So we're stopping with the limits. We're stopping with continuity. Now what we're doing is we're starting to step into derivatives. Okay? We're going to start slowly into derivatives. So the difference quotient is, let me write it first. And I'm going to show you what it is graphically. So let me take this off. Do you remember it? Yeah. It's not too bad. All right, I'll give you that one. Okay. So let me make this smaller so I can work with it. Okay. So I'm going to use this section down here. Okay. So we already know that this line is f of x equals 2x. Okay. That's the equation of that line. So what do you know about that? What do you remember about linear equations? Okay, and what are you talking about? What's it called? What did you just do? The rise over the run. The slope, right? That's what you did. You just talked about the slope. Well, it's what? Kind of, yes. So here's basically what this is. So remember when you were way back when you were young and silly and thought this was hard? we have 10 steps down or rise, and we had 5 steps over, right? That's where we get the 2, 10 divided by 5, right? And it's a positive slope because it's increasing, right? We're rising with everything. So it's an increasing slope, so that's why it's positive. Well, what the difference quotient does is it allows us to get to the point where we can find the slope of any function, anywhere. I could even have a function that looks like that. I can find the slope of it, okay, using the difference quotient. Well, what the difference quotient does is it leads us into the limit of the difference quotient, which is the derivative, okay? So derivative, what you need to remember, no matter what, is derivative is just slope. That's all it is. So derivative is how things change over time. That's what it is. That's what slope is. So remember, because we're in business calculus, we're talking business. So it's how prices change over time. It's how consumers change over time. It's how the industry changes over time. All of that is slope. It's how things change over time. The difference between linear equations and that kind of average slope, right? If I found the slope between these 2 points, that would be an average slope, okay? In calculus, because we're talking about a moving target, I can find the slope at an instant, at a very specific point. So in business, if I want to know, okay, what did the price do on June 6th, I better get up in the 2019. I can pinpoint it. And that's the beauty of calculus, because it pinpoints things. It allows us to hit a moving target, because our profit and losses are going to change, right? Every day there's a high and a low. We're seeing it in our economy, right? It was doing really good, and then it took a dump, and then now it's building again, and then it's going to go down, and it has to adjust, right? If it kept going, the worth of our dollar would go down. So it has to adjust as it goes. It's going to continue to rise, but it's going to go up and down. So what calculus does is it allows us to hit those moving targets and find instantaneous rate of change, okay? Instantaneous slope. So what the difference quotient does is it allows us to see it. So what we're going to do is I'm going to call, let me redraw it. I'm going to call this x, okay? I'm going to call this value x plus h. This right here, this little section, this distance in between, is h, okay? So we're going along, there's our graph. Oh, please. There's our graph. I have a point at x, and I have a point at x plus h. Okay? I want it to get closer and closer and closer and closer together. So as these points merge to each other, and as h gets smaller and smaller and smaller, I can start really pinpointing the slope. Or if my point is here, I can really start pinpointing the slope. So that idea of a limit as things are approaching, right? They're getting closer and closer and closer together. That's where all of that comes from, because we're trying to get this h value to be very, very, very narrow so that we can pinpoint and have an instantaneous rate of change, an instantaneous slope, okay? So here's where this comes from. This right here, this value right there, is called f of x. Agreed? Okay. What's this value right here? F of x plus h. Good? Now, if I want to find the slope between those 2 points, and we don't know, we don't care what h is at this point. We don't care. We know where we want it to go. We want it to go to 0, right? We want it to approach 0. But right now, we don't care. It's some random amount. If I was trying to find the slope between these 2 points, what would this one be? What would this distance be? I know this is... So if I wanted the slope between this point and this point, okay, this point right here and this point right here, and this is called f of x plus h. This is called f of x. How would I find this distance? What would I do? Yeah, I would subtract them, right? Remember the slope formula? y2 minus y1 over x2 minus x1, oops, x1. Remember, you just subtract the two. Well, that's what I did here. That's what that is, right? It's this one, this y value, minus this y value. All right, now where does the h come from? Well, if I'm going to continue with my whole y2 minus y1, x2 minus x1, well, I'm going to take this, because now I'm looking for this distance. So how do I find that distance? I subtract the two, right? Subtract my y's, subtract my x's. Well, watch. If this is my x and I'm subtracting off the x, what am I left with? Just the h. That's where the h comes from. Okay? It's slope. That's all it is. It's just slope. So watch the beauty of this. We're going to use that function, 2x. You already know what the slope is. What's the slope of that line? 2. Let's prove it. Watch. Every time I see an x, I'm going to replace it with x plus h. Every time I see an x, I'm going to replace it with x plus h. That's what that says, right? That's that functional notation. It says take out your x, plug in x plus h. Then it says subtract off my function. Okay, so whatever the function is, I'm going to take it off. Right? And then I'm going to put the whole thing over h. Okay? So now I'm cleaning it up. Now it's just algebra. The minute you have that x plus h in place and then you're subtracting off the original function, you're good to go. You have all the tools you need. You're just doing algebra. So I'm going to distribute this x through, this 2 through. And then I can cancel my 2 x's. And I end up with 2h over h. So what happens to the h? They cancel. What's left? 2. It's the slope. Okay? So this shows, okay, I already knew it was 2, but this shows that I can algebraically, using the difference quotient, find the slope. So now let's do one that's a little bit more difficult. So get out your, this will be the last thing. Get out your homework from your number 1 homework, and we're going to do that one problem. I can find it. Let me erase all this. Okay, so the problem is, where to go? 2x squared minus 5x plus 3. Okay? All right, so the first thing you're going to do, you're going to take out every x and do what? What's it tell you to do? Yep. Put in an x plus h. Okay? So I'm going to take out my x, and I'm going to plug in x plus h. I'm going to take out my x and plug in x plus h. No, you're going to FOIL it first. So here's a shortcut. So I know I taught all 4 of you this. This is what turns out to be a perfect square trinomial, right? So do you remember the shortcut? Square the first one. Square the second one.
And then it's going to be 2x.
Yep, and it's going to be multiplied and double it. That will always be that. every single time. So you don't have to refoil it every single time. Square the first one, multiply and double, and square the last one. Okay, now if you don't trust me, you have trust issues, and you want to do it yourself, you can actually do FOIL, and that's what you'll get. Okay, so I'm trying to save you a step. It's going to be this every single time. So you're going to go 2 times x squared plus 2xh plus h squared. And then minus 5x minus 5h plus 3. So this is just algebra skills. That's all it is. It's just keeping track, making sure you're multiplying everything through, you're distributing everything. Okay, so this is this. That's all I did. So what else do I got to do? Got to subtract off the original. Now be careful, because you're subtracting off that whole thing. Don't forget to put it in parentheses. And these are long and drawn out. I get it. But they're fun because you get to scratch out a bunch of stuff. So when you subtract off the whole thing, that means that all of these signs change. And then you can get rid of the parenthesis. You just switch the sign because you're subtracting. And then you should be able to cancel. So my 2x squared is going to go away. My negative 5x, positive 5x, positive 3, negative 3. If you can't do that, then you did something wrong. That should be a huge red flag. Everything should cancel except terms with h's in it. So I have 4xh plus 2h squared minus 5h all over h. Now what? Now you got to factor out an h. Now, it's kind of one of my pet peeves. You can't just go through and cancel h's. You'll get the same thing, but it doesn't, it's algebraically incorrect because you can't cancel when there's pluses and minuses. You can only cancel when it's all multiplication. Okay? Now, go ahead.
Is that your answer?
Uh-huh, for now. Yep, for now. So watch. Minus 5x plus 3. Yeah. So this is the slope. The slope is, what did I say, 4x plus 2h minus 5? 4x plus 2h minus 5. What did we say h was going to do? What do we want it to do? Remember, h is that distance between the two x values. We want it to get smaller and smaller. So what is it approaching?
It's approaching 2.5.
Even less than that. It's approaching what? If it's getting smaller and smaller and smaller, right? It's approaching 0, right? I want that h to be so tiny that there's hardly any room in between, right? So it's approaching 0. So when h is going to 0, what happens to it? It goes away. What's 2 times 0? It's 0, right? It goes away. So look, you can find the slope anywhere on this graph. If x, this stuff is just too cool to me. If x is 0, what's the slope? Negative 5. Look. You see how the slope is going down? What if x was 1? What's your slope? It would be negative 1. Still going down. Oops. What I'm doing is I'm putting it right, I'm putting the slope of my line, which is called a tangent line, right? It's a tangent line. It's the slope of the line right at that point. So at x is 0, here's x is 0.